So the big topic today is going to be infinite limits, and we're going to start by looking at two graphs. The graph g of x, which is given by 1 over x minus 2 squared, and f of x, a nice piecewise function, which is x plus 1 if x is greater than 2, and just going to be x if x is less than or equal to 2. So let's look at their graphs. So as we look at their graphs, they are quite different, but what we can do is we can notice that at 2, there is something similar going on between them. At 2, the limits don't exist. But the limits don't exist for very different reasons. If we look at the graph on the left, even though both sides are coming up together, they're not coming up to a simple number, they're going off and they're just getting bigger and bigger and bigger. Whereas on the right, our graph from one side comes to a number, and from the other side comes to a number as well. And so for the graph on the right, what we said was that we have the limit as x approaches 2 from the left-hand side is definitely going up and getting close to the number 2 here, whereas for the other side, that should of course be a plus there, as we come in from the positive side, we're going to get close to 3. And so we do sort of have limits here. We don't have a total limit as we approach 2 because they're different numbers, but we have a limit from the left and a limit from the right. And what we want to do in this section is talk about a way to make sense of the limit for the graph here on the left. And so what we're going to say is we're going to say that as we get closer to 2, this limit approaches infinity. So our notation for this will be given as the limit as x approaches 2 of g of x equals this symbol called infinity. And we'll say that the limit approaches infinity, which is a nice fancy way to say that the numbers keep getting bigger and bigger and bigger as we get closer to 2. So now for our more formal definition, a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit, whether or not it gets bigger or smaller. And we have two notation styles. One, if it just equals infinity, this indicates a function that keeps getting bigger. So this was our previous example from both sides. As we get closer and closer to the value of 2, we're getting bigger. Whereas what could also happen is we could also have the case where we're getting smaller and smaller, more negative, and this would be decreasing without bound. So a good picture to keep in your mind of this one is just the opposite direction. In this case, our limit is going off to negative infinity here. And of course we can do everything here with limits from the left, limits from the right, plus or minus infinity. And so we'll look at an example of that next. Now if we look at the function here, f of x equals 1 over x, and we look at the graph, we said before that if we tried to take the limit as x approaches 0 of f of x, it still does not exist. That is, it's not getting closer to a number, therefore it does not exist. However, we can now apply the ideas of what happens as we approach from the left and the right. So we can make sense of the idea that the limit as x approaches 0 from the left of this function will indeed equal negative infinity. And this is because if we follow the function, as we get closer to 0 from the left, we are going down. We're going to keep decreasing without bound. Similarly, we can make sense of the limit as x approaches 0 from the right of f of x. That is, in our graph, if we tried to substitute numbers in, well, these numbers are going to keep getting bigger and bigger and bigger. Therefore, they're going off to positive infinity. So this indicates that the values keep increasing as we put numbers in that are closer and closer to 0. Now a quick word of warning, these limits do not exist, okay? We're only going to say a limit exists if it goes towards a number. Rather, they're just notation to indicate that either we're getting bigger or we're getting smaller. It doesn't actually exist as a number. We'll do a few more examples of computing infinite limits without graphs in a second. But first what I want to do is I want to take a little break to talk about something interesting that occurs with infinite limits, and it's this vertical line here that occurs in between them. So the function is getting closer and closer to this vertical line, but it never hits it, and it's so important that we give it a special name. So we're going to call this line that our graph gets close to but never hits a vertical asymptote. So our technical definition, when we graph functions with infinite limits at c, and we see that the graph approaches a line defined by x equals c, this line is called a vertical asymptote. So it's very important, it's not an asymptote, It's an asymptote, okay? So the line here on this graph, so here was our example before of f of x equals 1 over x minus 2 squared. And we said that the limit is going to infinity as we approach 2. So this means this vertical line here at x equals 2 is a line we get closer and closer to, but we never hit. So it's very important to remember that graphs do not go through vertical asymptotes. There are definitely barriers there in the way that your graph should not go through. It's going to get close. It's going to get darn close. It's going to get as close as possible if you continue drawing your graph vertically, but it will never actually hit that line. So here's a theorem that tells us how we can go ahead and find some vertical asymptotes if we have a function. So let's suppose we have f and g, nice continuous functions, on an open interval containing a point c. If f of c is not 0 and g of c is 0, and there exists an open interval containing c such that g of x is not equal to 0 for all x of c in that interval, then the graph of the function given by h of x equals f of x divided by g of x has a vertical asymptote at x equals c. Okay, so this isn't the clearest thing in the world, but let's go through and see what this is really saying. Basically, what I want to do is I need to find a c so that g of c, my denominator, is 0, and my numerator, f of c, is not equal to 0. And if this happens, I'm going to have a vertical asymptote. So let's go ahead and try to find all vertical asymptotes of our function f of x equals x squared over x squared minus 4. So step 1 is to find all numbers that are going to make your denominator equal to 0. So if we set x squared minus 4 equal to 0, well, what we can do is we can factor as x minus 2, x plus 2 is equal to 0. So this means that x equals 2 and x equals negative 2 are possible vertical asymptotes. Step 2, according to the theorem, says, well, if this number makes the numerator non-zero, then you're going to have a vertical asymptote. So now we need to check these numbers. We need to check them in the function x squared. So we check this. So we see, well, let's see, 2 squared is equal to 4, and negative 2 squared is also equal to 4. So this means x equals 2 and x equals negative 2 are going to be vertical asymptotes, often abbreviated by VA. So doesn't seem so bad. It's a nice quick way to check if we have vertical asymptotes. They cause basically divide by 0 problems, but it's not a 0 in the numerator. So while this seems pretty easy, let's try a few more examples to see what could happen. So now suppose instead we have our function g of t is equal to t minus 1 over t squared minus 1, and we'll follow the steps from before. So we start by finding the values that make our denominator equal to 0. Well, if t squared minus 1 equals 0, we can factor this as t minus 1 times t plus 1 equals 0. So this means t equals 1 and t equals negative 1 are possible vertical asymptotes. Step 2 says, well, we need to check and see if this makes our numerator, in this case t minus 1, equal to 0 or not. So we go ahead and we check, and we see that, well, negative 1 minus 1 equals negative 2, so that works out. T equals negative 1 is indeed a vertical asymptote, but 1 minus 1 is equal to 0, and our theorem doesn't tell us anything. It doesn't tell us if it is an asymptote or if it isn't. So what this tells us instead is if this number makes the numerator 0, then we need to try something else. So what we're going to try instead, because we don't know about the number 1, is we're going to try computing the limit as t approaches 1 of t minus 1 over t squared minus 1. And as we saw, we can factor this into t minus 1 over t minus 1 times t plus 1, which then we can cancel using our nice limit theorem. Since limits don't mind canceling so much, we can go back and cancel. And we're left with the 1 over t plus 1. And now this is a nice rational function, so we can directly substitute and get 1/2. And so we see here, since the limit is not equal to infinity, this is not a vertical asymptote. So this limit is not a vertical asymptote. We still can't put 1 into our function, but we actually gave this a special name in the last section. Instead, we call this a removable discontinuity. So the limit exists here, it's just a hole in our function. It's not a vertical barrier our function can't pass. So now that we've gotten good at this, let's try one more example. So feel free to pause the video and try this one yourself. But here we go. So we have a function h of w is equal to w minus 4 over w minus 4 squared. So step 1, of course, is we need to figure out, well, what's going to make this denominator equal to 0? And remember, w minus 4 squared is fancy talk for w minus 4 times w minus 4 equals 0. So in this case, w is only equal to 4. We check it in the numerator, w minus 4, which tells us 4 minus 4 equals 0. So according to our test, well, shoot, we're inconclusive. We don't know what to do now. This could be an asymptote. It might not be. So let's check and see what happens. In this case, we try something else, and we say, well, let's compute the limit as w approaches 4 of this function. And this function's already nice and factored for us. So we see what happens. Well, the limit is going to be 1 over w minus 4. Well, this limit actually is not going to exist, and we want to think about why. Well, let's compute the limit from one side. The limit, as w approaches 4 from the right, of 1 over w minus 4. Well, what's going to happen here? Well, our numerator is just going to be 1. Our denominator, if we put in numbers that are slightly bigger than 4, so I'm talking like 4.1, 4.01, 4.0001, I'm going to get really small positive numbers. So what this means is I'm going to end up with a 1 over really small positive numbers, which tells me my limit's going to be infinity. If I try to take 1 and divide by really, really small positive numbers, those numbers are going to be really, really big and make me go off to infinity. And so this is also a good notation style to use for this style of limits. We're going to use it again in the next few problems to compute some limits. But overall, what it tells us in this part is that w equals 4 is a vertical asymptote. In this graph, what's happening is as we approach 4, we are going off to infinity. The test didn't work so well, but computing the limit did tell me that it indeed was an asymptote. Step 1, though, is always useful because it tells us sort of where to look. Step 1 tells us candidates. So these are things that we either need to try in the numerator or try to find the limits of. So here we have a number of properties of infinite limits that are going to help us when it comes to compute limits that go off to infinity. So we have that let c be any real number, that is, this is the number we're going to approach in our limit, and L is also a real number. And we want f and g to be functions, so that we've already computed these some other time, and we know that the limit as we approach c of f goes off to infinity. It has an asymptote there. And we know instead that g, though, just goes off to some number. Well, what these properties tell us is sort of a little bit of the way that you can do some arithmetic with infinity. The first one is the sum or difference formula. It says that if we take the limit of a function f that we know is going off to infinity, and g, which is going to be a number, this is going to be infinity. This is because infinity plus or minus some number is still going to be infinity. Really big numbers are unaffected by small, puny, not infinite numbers. The product rule says that infinity times a number will either be positive or negative infinity. At most, what's going to happen in this case is L will either make this stay positive or become negative. And last is our quotient rule. If we take L and we try to divide it by a big number, really, really big number, well, this is going to be 0. That's because, if you divide anything by a large enough number, it gets really, really small, so it gets close to 0. Now, these properties also hold pretty similarly for negative infinity and one-sided limits. There's just going to be changes of plus or minus. Now, the big thing with these properties of infinite limits is that a lot of these require a lot more conceptual thought than just substituting and canceling numbers. So let's see some examples. So let's look at, suppose we want to compute the limit as x approaches 0 from the left side of x squared minus 1 over x. Well, what we can do is we can break this up and we can say, well, I know that the limit, as x approaches 0 from the left, of x squared is just going to be 0. This is a simple polynomial, so I can just directly substitute in 0 squared and get 0. No muss, no fuss. I can also compute the limit, as x approaches 0 from the left, of 1 over x. We've seen this example before already, but essentially what's going to happen is we're going to get 1 divided by a very, very small negative number, which indicates that overall this number is going to be negative infinity. Dividing by the small negative number is what causes the negative infinity. So what do we have going on here in our limit? Well, this means our limit here is going to be 0 minus negative infinity, which overall is going to be positive infinity. And also, this is a really good amount of work to show for this problem. And we can see that this is really just use of property 1 up here in our table. That is, 0 minus a negative infinity will give us infinity. So take a minute to try to compute this one yourself. So hopefully what you did is you looked at this and you thought, this is just a trick question. This is a nice rational function, which means I can attempt to directly substitute. So I put 4 into the numerator, 4 in the denominator. I go through my arithmetic and I get, well, 16 over 32 is 1/2. No infinite limits, no tricks around here. Don't be obsessed with infinite limits, just be wary of them. So now, what if we're faced with something like this? Well, again, what we can do is we can look at this and we can think of it in terms of trying to compute two separate limits. Let's compute the limit as x approaches pi over 2 from the right of just -2, and the limit as x approaches pi over 2 from the right of 1 over cosine of x. So the first limit is fairly easy. It's just a constant, so this is just going to be -2. Now this second limit gets a little bit more interesting. The 1 is just going to get closer and closer to 1, but we want to think, what is cosine doing as we get closer to pi over 2 from the right? And in this case, you either have to think back to the graph or think through this, but in this case, what's happening here is this is getting close to 0, but from the negative side. This is very close to 0, but so this is a small negative number. So overall our limit over here is going to be 1 divided by a small negative number, gives me a negative infinity. So overall the negatives cancel, and I'm just left with a final answer of infinity. Once again, these are good things here in order to show your work. If you want to get partial credit, if you want to get any credit, you need to show your work. So we're going to try one last example here. So pause the video, take a second to try this one on your own before we discuss it. So hopefully you didn't do the following. Many students, when they first see infinite limits, they try to rush and go a little quick, and they say, well, if I look at my denominator here, and I put in a number that's a little bit bigger than 2, this is going to give me a small positive number, therefore dividing by a small positive number is equal to infinity. The problem is, this is totally wrong. What we really want to do in this limit is we want to see that this limit here, we want to notice that we didn't get 0 in the numerator if you plug in 2. Instead, what we want to do here is we want to factor. Because if we factor, we'll see that the numerator factors nicely, and it factors in such a way that we'll be able to cancel with the x minus 2 in the denominator. What we really have here is a removable discontinuity. And so what we get for our limit is instead the nice limit as x approaches 2 from the right for a nice polynomial function, which allows us to directly substitute and get 4. Don't be misled by these, okay? So you really have to think through these very carefully to see what happens and to make sure that you're not trying to divide 0 by 0, because that's probably a removable type, though it might not always be. So really think through these, work through these carefully and very slowly. And also always feel free to throw it in a graph and see if that matches the work that you've done algebraically. There is a handout on Blackboard, otherwise you should have gotten it in class yesterday, and please be sure to post a question to the question sheet. Thanks.